Let's look at information extraction in natural language processing. We know that text comes in the form of unstructured data, and we want to extract information from that data by using natural language processing. If you ask Gemini, as of 2024, in the vast realm of unstructured text lies a treasure trove of valuable information waiting to be unearthed. Information extraction, a fundamental task in natural language processing, empowers us to unlock this hidden knowledge by transforming raw text into structured data. By delving into the semantic content and meaning of text, information extraction enables us to discover and extract key insights, relationships, and entities. This series will embark on a comprehensive exploration of information extraction techniques, shedding light on the methods and algorithms that enable us to extract meaningful information from the written word. I just noticed the typo here, so even our AIs can sometimes make mistakes. Digging into information extraction tasks, I will start with named entity recognition. Effectively, we want to take text which is unstructured by nature and add some structure to it so that we can extract information from it to gain knowledge. One of these tasks, named entity recognition, will give us some of this knowledge that we want to extract from the text. Here we want to identify entities, just as the name implies. Named entity recognition recognizes entities within the unstructured text. These entities might be things like names of people, places, companies, or proper nouns. It could also be dates and times, amounts, quantities, or in particular domains, we might have entities that are specific to that domain. For example, in the omics studies, genomics, proteomics, we may want to identify entities that represent genes or proteins and so on. In the case of social media, when looking at social media data, we might want to identify entities that represent usernames, their profiles, their pages, and so on. These are just examples of types of entities we may want to recognize using named entity recognition. Let's look at an example of doing named entity recognition using a large language model. For that, I'm going to go to Hugging Face. And if you were like me and using dark mode, I apologize for the screen suddenly going very bright. I found it shocking as well. We go to Hugging Face and search for named entity recognition. We see there are over 8,900 models that are trained to do named entity recognition. I'm going to sort these by the most likes. And we'll just visit the first model on the list. And we see that this is a model that was fine-tuned from BERT base to do named entity recognition. In Hugging Face, with many models, you can directly test the model using the Inference API. And in this case, we see an example of a string of unstructured text that says, "My name is Clara and I live in Berkeley, California." When we run this model, we get the named entity recognition that Clara is tagged as a person, Berkeley is tagged as a location, and California is tagged as a location. So named entity recognition looks a little bit like part of speech tagging, only now we're tagging for entities rather than the grammatical parts of speech. Go back to our lecture notes. In addition to identifying entities, we need to be able to determine when different entities refer to the same entity. We call this reference resolution. For example, in your text, you have recognize the entity John. And later in the text, you see John Smith. And at another point in the text, you see Mr. Smith. We want to resolve all of these to the same entity. That is, we want to identify that each of these mentions refers to the same entity. Methods for performing reference resolution include entity clustering and co-reference resolution. In entity clustering, we handle things like the named references I mentioned. And in co-reference resolution, we handle things like pronouns. If we see the pronoun, for example, he, who does he refer to? Does it refer to the entity John Smith? The linked article here gives an in-depth look at co-reference resolution. And this can lead to, of course, substantial information gain. I linked to this article so that you can dig deeper into co-reference resolution and some of the problems associated with it. This is a nice read. Of course, there are ambiguities across named entity recognition in general, and these pose challenges. For example, there could be multiple entities named John. Here the entities have the same name and they're the same type of entity, but they're not the same entity. There's also the case where different entities can have the same name, but not be the same type. And the example I have pictured rather crudely here illustrates that, where we have Paris, which is a city in France. Paris is also a casino in Las Vegas. Paris might also be a person. So there's clear ambiguity here because the same label is attached to different entities, and in addition, those different entities are different types of entities. Of course, these ambiguities pose challenges in named entity recognition and require advanced techniques to resolve them. General techniques for named entity recognition include sequence labeling, which involves training a classifier to label tokens with tags. Again, similar to part-of-speech tagging, but now we're looking at entity tagging. And the process looks something like this. We start with an input of structured text. We perform some human annotation on that text to build data for supervised training. We encode the text and perform feature extraction to prepare the data for training. We split the data into a training and testing set, possibly an evaluation set as well. And we train some form of labeler or large language model in the case of the Hugging Face model we just looked at. For traditional machine learning models, you can go to scikit-learn and look at the classification techniques that are available. This is a common machine learning library in Python. And you'll see a lot of techniques for supervised learning that can be applied to this problem. In addition to named entity recognition, we may also want to perform relation detection and classification. Here we want to know what are the semantic relations between these entities. Examples of that would be like your family. People in the same family are going to have a familial semantic relationship, or consider the relationships among companies and employees, or memberships in different groups and organizations, and so on. There could also be semantic relationships that are geospatial in nature, people who go to the same places at the same time, or live in the same town or in the same geographic region. In general, any parts of a whole encompass a class of relationships, and all of these are types of relationships we want to be able to capture. This might sound familiar if you think about things like relational databases or object-oriented programming. To build these relations, we need a way to identify them in unstructured text. Techniques for approaching this task may again use supervised learning, where we extract features of the named entities, detect the presence of the relation, train a classifier to make a, for example, binary decision of the existence of the relation between pairs of entities, and then train the classifier to label the relations using a multi-class labeling and classify the relation. We also want to be able to detect and classify events. These are expressions in unstructured text that denote an event or even a state that we can assign to a point in time or an interval of time, like things that occurred at a particular point in time or things that continued over some period of time. These might be identified using rule-based or statistical methods. And again, just like we did with named entities, with the events, we have to do reference resolution. We may have different mentions of the same event with slightly separate expressions, but they refer to the same event. And we apply reference resolution to recognize or classify these events together. We also want to recognize temporal expressions for temporal analysis. These could be precise, like a specific date or a specific time, or they can be relative. For example, 2 days ago is a temporal expression. And we, of course, want to associate that with a specific date and time. To do that, first you would have to identify what the base day is that this is referring to, and then subtract 2 days from that. In order to do this, we first want to perform normalization on all of the temporal expressions that we've located. We may use something like ISO timestamps, which is a specific format of timestamp that is widely used, and fit all of our date times to match this format, thereby fixing temporal expressions to a date and time anchor. And finally, given these events and the timestamps that we now have, we can associate the temporal expressions with events that we detected in event detection. By doing so, we can organize events in a complete and coherent timeline. This is a very useful task in natural language processing. We started with unstructured text, identified all of the named entities, the events, the times, and we're able to build a timeline of a story. And now we have some really good structured texts that we can derive information from or perform further analysis on. In order to perform tasks using machine learning, we start by doing some common pre-processing steps to clean and normalize the raw input. Remember, our raw input is unstructured text. Some of these steps are outlined in this code I've provided. The actual steps we need to do to pre-process our text is going to vary depending on a lot of things, like what is the input text? What does it look like? What kind of data is in there? What are the information extraction needs? What do we need the output to look like? What types of analysis are we planning to run on that output? If we're doing some machine learning or supervised learning techniques, what do those techniques require? What do the inputs to those techniques require so that we can format our outputs to match those inputs, and so on? These types of things will dictate the pre-processing that we need to do. In this simple example, I look at some typical steps. For the example, I chose a test sentence that may demonstrate a challenge for co-reference resolution. Recall in co-reference resolution, we want to take things like pronouns and associate them with the entities that they represent. In this test sentence, the captain's ferret escaped. If you see him, report to him immediately. One him refers to the captain, the other refers to the ferret, and it might not be clear which is which. If we see the ferret, are we to report to the ferret? Or if we see the captain, are we to report to the captain? Or if we see the ferret, are we to report to the captain? And it's not entirely clear. As a human reading this, as an English-speaking individual, you might immediately recognize which pronoun goes with which entity, but that may not be entirely clear to a machine that's reading this. So things like context would need to be looked at in order to make that determination. So that is the example sentence that you can use in this script to show you how to do a little bit of text pre-processing, and just an example. So in the text pre-processing steps, so I have this method, simple clean, and I'm going to send my test sentence to the method. And in the method, the first thing I'm going to do is convert all of the text to lowercase. I'm going to remove digits and special characters. Again, depending on what you are actually attempting to do, you may or may not want to remove those, but it's something that is commonly removed prior to employing different machine learning techniques. Then I use the NLTK Natural Language Toolkit library from Python to tokenize the sentence into tokens, which are the primary form of data that we like to input into our machine learning algorithms. I remove stop words using the NLTK library again, and the stop words list, which identifies words that don't provide a lot of information in terms of understanding the text, and we can safely remove those and want to remove those before applying some machine learning techniques. We may need to also take into account any misspellings in the text. So while I do not have a particular example of a method to use for handling misspellings, I note that at this point you may want to take care of any misspelled words. And then perhaps perform stemming or lemmatization, something we looked at before, where stemming reduces words to their common stems, and lemmatization is a little more advanced, where instead of just reducing a word to its stem, it actually recognizes different verb forms. In this case, I used lemmatization, and then I take my tokens from above and apply lemmatization to them, and that cleans my text. And an example output of what that clean text looks like is provided here. Captain Ferret escaped, see report immediately. That is just a simple example that you can copy and run to practice with pre-processing tasks, which are certainly necessary to perform machine learning against our unstructured text in order to perform some of the tasks mentioned here.